So everyone's seen enough visual illusions to know that the things that we see are not exactly reflections of the stuff that's coming in and hitting our retinas. And back in the 1930s, James Gibson was doing some of the early work to try and see how it is that we can learn about the biases in our visual system by looking in high detail at what illusions really tell us. So one of the things that he noticed was this thing that is now termed the tilt illusion. I made a quick example so that you can get a sense of the way this works. So try and keep your gaze focused on that plus sign in the middle of the screen. As you stay focused, try to see if you detect any subtle rotation in the center disk, and try to ignore the obvious rotation in the exterior disk. For many people, what you're going to end up seeing is that that center disk starts out tilted just a little bit to the counterclockwise direction of vertical. And then as the outer disk is rotating, maybe you see that center disk start to waver a little bit. It might move even a little bit more counterclockwise, then come up to be almost entirely vertical before drifting back to being counterclockwise again. Now, as I told you, this is an illusion, so you might have guessed, actually that middle disk doesn't move at all. What's going on is your brain is trying to make sure that the center disk and the exterior disk stay separated. It's trying to bias your representation of the two disks so that their orientations don't interfere with each other. So when the outer disk becomes close in orientation to the inner disk, you start warping your perception of the inner disk so that you can keep them separate. It's a way that the brain allows us to keep different objects separate in the visual world, especially in the jumbled mess that is the actual visual experience of everyday real life. So obviously this is a little bit disconcerting. It's always disconcerting to have illusions shown to us. We'd like to think that we have a veridical experience of the real world. But what happens to the information next? What happens once that information has been processed and reached perception? We'd like to think that that's it. Once it's in perception and we're focusing on it, the information's not changing anymore. But the research I'm going to show you today from Paul Scotti working in Julie Golam's lab shows us that actually information that can change even while you're focusing your mind on it and trying your best to hold it stable. And specifically, they found something that was pretty similar to the tilt illusion. They found that your brain is always trying to keep information separate. So if you're trying to hold two things in your mind at the same time, and those two things have a risk of interfering with each other, you can bet that your brain is going to bias your representation so that those pieces of information actually become more different from each other, even when they might not have been that different to start with. Hi there, my name's Adam Dede, and welcome to a Neuroscience Journal Club, where I bring you a weekly discussion of a recently published article in the world of neuroscience. So obviously there's illusions in our visual perception. I think everyone is pretty aware of that. But I think the general intuition is that information that you're currently focusing on, that you already have in perception, is going to be relatively stable. There's not going to really be any warping in that information. And what's more, things like the tilt illusion that we just took a look at are things that happen in a really automatic way and happen when there's multiple pieces of information that are competing with each other. We know, of course, that if you just have one piece of information, then it's not going to be too hard. So basically the point I'm trying to make is that as long as you have a good chance to look at and really memorize a stimulus, then once it gets into perception, you can hold it in your mind and keep it stable, no problem, right? The question, though, is what happens when there's two items in mind? After all, the tilt illusion that we just looked at, it happens only when there's two different oriented gratings that you're trying to perceive at the same time. So is there going to be something like that that happens when you're trying to hold in memory two different pieces of information at the same time? And so that's exactly what Scotti and colleagues set out to try and look at. And they performed 4 experiments where each of the experiments had basically the same general flavor. So participants would see a pair of everyday objects on the computer screen, and importantly, all of the objects had their colors changed so that every pixel in each object would be either white, black, or some single color. So the participants' task then was to try and memorize the two object color associations that were represented by the two objects and their two colors. Then they had to hold that information in mind for some period of time, and then one of the two objects would be presented with its color having been removed, and the participant would have to use the mouse to click on a color wheel and indicate what color they remembered the item as having been associated with. Now, critically, this gives us a really nice way of judging the accuracy of the participant, because we can see that they might be generally correct, but we can also see exactly how far off they are in a really quantitative way, which gives us a nice measurement. So in the first experiment that they did, the delay that the participants had to keep the object association or the object color associations in mind was only 1 second long. So if it's the case that objects in memory systematically bias such that we try and separate the representations of things that are in our memory, then we should see that representations of colors that people remember are systematically further away from the other color that's being held in memory whenever memory is tested. So for example, imagine that you're trying to memorize that object A is orange and object B is yellow. Now, if you remember the rainbow, Roy G. Biv, then what should end up happening is that the orange item becomes a bit more red and the yellow item becomes a bit more green. If this were to happen over and over again when people are demonstrating their memory, that would be evidence to us that there's some kind of repulsion bias going on in memory. The two items are getting repelled from each other. But that's not what Scotty and colleagues found. So on the graph that we're looking at here, negative values along the x-axis represent repulsion bias, and positive values represent attraction bias, which we haven't talked about, but is just kind of the opposite of repulsion bias. So on the y-axis, you can see the probability of various bias values. And these probabilities are calculated using a computational modeling approach that's a bit beyond the scope of this video. But the key thing to understand is that these probabilities tell us how confident we can be that participants had various levels of bias. The green distribution is showing us how much probability there is across a range of bias values. The peak of the distribution is at about -1, implying a trend towards a repulsion bias. But what the box and error bars down on the bottom is showing is the middle 95% of the probability distribution. The fact that it includes 0 tells us that there's a reasonable chance that there was no bias at all. You can see the individual participants represented by the dots, and notice how although most of them are on the negative side, many of them are on the positive side too. All in all, this tells us then, although there was a numerical trend towards a repulsion bias, there was not strong statistical evidence for it. So they did a second experiment. And the only difference between the first experiment and the second experiment was that in this second experiment, the memory delay that participants had to hold the object color associations in their memory was 3 seconds as opposed to 1 second. So if it's the case that actively holding things in mind causes them to drift apart over time, then now we might see a repulsion bias where before we didn't see one at the short delay of only 1 second. And indeed, that's exactly what they found. So here, you can now see that the peak of the probability distribution is near -2, and the error bars don't reach anywhere near 0. And very few of the individual dots are above 0. The two colors were repelling each other in working memory. And further, if we think about experiment 1 and experiment 2 and comparing those results, we can think that it's really happening in working memory. It's not happening in initial perception, and it's not happening during remembering or reporting memory. Because if it was, then these things weren't different in experiment 1 versus experiment 2. So something about holding information in mind causes that information to repel against itself, such that items that are being held in memory become more and more separate over time. And this does seem like it's something that could be helpful, helping us be able to keep items separate in mind so that we don't get confused. But at the same time, it's an indication of a fundamental inaccuracy in the way that our mind works. Scotty and colleagues wanted to replicate and check, make sure that this really is what's happening, and so they wanted to compare this 1 second condition to the 3 second condition in a more head-to-head way. So in the third experiment, they had 1 second conditions and 3 second conditions kind of interspersed, mixed in amongst each other in such a way that the participants couldn't predict exactly how long the memory delay was going to be on each individual trial. This was important because if the participants had some kind of an anticipation of exactly how long each trial was going to be, then there might have been weird ways that they were accounting for that, which might have been causing the effects that we're seeing, rather than an actual repulsion bias going on in memory. But it turned out that they replicated the results that they'd found in experiments 1 and 2 really pretty perfectly. And you can see that here on this graph. So when participants had a long delay of 3 seconds, shown in orange, they exhibited a repulsion bias. But then when the delay was short, shown in green, they did not. And the researchers checked to see if this was caused by weaker memory, but it wasn't. In the 3-second condition, memory was about the same strength as memory in the 1-second condition, which again makes sense. If you're asked to hold something in mind for 1 second versus holding something in mind for 3 seconds, it's not really that much more challenging to hold it in mind for 3 versus 1. So even though participants were exhibiting these shifted memories, these biased memories, they weren't exhibiting any evidence of increased guessing or any total misses. It was like that little bit of orange to red shift that we talked about earlier, but it wasn't like an orange stimulus was being remembered as purple. No big errors like that. So all of this really does seem like there's something very similar to the tilt illusion going on, but in memory rather than in perception. And it brings up the immediate question of mechanism. What exactly is going on under the hood that's making this happen? So Scotty and colleagues did a 4th experiment in which they tried to look at this a bit. In one version of the task, participants had a 3-second delay, which was exactly the same as the 3-second delays that we've talked about in these previous experiments. But in another condition, participants had to do an extra task, a distraction, during that 3-second period. And specifically, they were showing 2 grayscale images, and they were asked which of these items shown in the images is larger in real life. And by doing this, participants would have some kind of a distraction which might interfere with any kind of active working memory processing. The idea being that, does active processing of information cause the repulsion bias, or does the repulsion bias happen in a more automatic way that doesn't matter if the participant is actively engaged in processing the information? As you can see here, the data from the condition with no filler, shown in orange, cleanly replicated the roughly 2-degree negative bias that was found in earlier experiments. But the data from the condition with a filler, shown in purple, gave no evidence for a bias at all. Unsurprisingly, though, participants in the filler condition had less accurate memory. And specifically, only on 72% of trials were they able to report a color that was even close to the one that they were trying to remember, where, by contrast, on the no-filler condition trials, participants had an 85% accuracy. So this leads us to something of a counterintuitive finding. In the condition with the filler, participants had lower ability to remember the color at all. But when they did remember the color they remembered was more specifically accurate than in the no-filler condition. By contrast, on the flip side, in the no-filler condition, participants were able to remember the general color much more frequently, 85% of the time. But when they remembered it, it was corrupted. They had this repulsion bias going on, which caused them to have colors that were constantly biased and slightly shifted. So it's really kind of a crazy phenomenon that's going on here, where you can have an increase in accuracy by focusing on the information that you're trying to remember, but a decrease in specificity. So it's a little bit of a strange finding then. The more that we actively focus on a piece of information, the more that piece of information will actually get degraded or biased as it's worked on by our brains. And this seems like it's not really the way that it should work. Why would brains evolve to do that? But I think here again we have to keep in mind that brains aren't trying to be veridical recorders of the exterior world, and they're not even necessarily trying to encode the variables that we think they're trying to encode. What they're really trying to do is help us make adaptive decisions in the moment and in the future. And sometimes doing that does not actually mean that it's best to have an accurate or perfect representation of what's going on in your perception. You want to have something that accurately separates the important information from other important information. You don't want to get confused or have interference effects going on. And that can be more important than having an accurate representation or a highly specific representation. In the repulsion bias example that we're talking about, I think it's really important to keep in mind then this trade-off between overall accuracy and specificity. Even though the participants in the no-filler condition had lower specificity because they exhibited this repulsion bias, they had higher overall accuracy. And sometimes that trade-off between having a certain amount of lowered specificity in exchange for a higher amount of accuracy might actually end up being the most adaptive thing. So Scotty and colleagues put forward a little bit of an explanation for what they think might be going on at the neural level, and they spelled it out in the language of center-surround lateral inhibition. The general idea is that if you have a particular neuron that represents, let's say, orange, it doesn't just do this by firing excitedly to indicate excitation towards the color orange. It also actually inhibits its neighboring colors. So when you have some orange stimulus hit the eye, you're going to get activation of orange representations, but you're also going to get simultaneous inhibition of red representations and yellow representations. And in this way, you can bring the representation for orange into sharp relief. So now, if we imagine that you have an orange representation and a yellow representation simultaneously, well, that orange representation will be inhibiting the yellow one, and the yellow one will be inhibiting the orange one. So if they drift further apart, then they can avoid each other's lateral inhibition, and in that way become clearer and cleaner neural representations as they are processed by the brain. But this is only going to happen in active maintenance, and not something that's going to happen passively or automatically. So once again, we can see an example of a situation where the brain tries to keep information separated, and it doesn't necessarily care if doing that means that it's representing information in the most specific or true-to-life way. So that's it for this time. Hopefully you're enjoying my improved sound quality coming to you from this black void. And please like, comment, subscribe, all of that good stuff. And if you're really liking the content, I'd appreciate it if you supported me on Patreon and share the videos with your friends. All right, that's it, and I'll see you next time. Bye.